p.m. India Standard Time. Good afternoon, everyone. Good afternoon from India. Good morning to everyone in Europe, and whatever it is in other parts. Good morning. Very odd time in certain parts of the world. I know we have delegates and speakers connecting from other parts of the world. Our sincere apologies, but a very warm afternoon, about 45 degrees Celsius afternoon in Pilani, Rajasthan, India. I'm speaking from BITS Pilani. I'm Shouvik Bhattacharya. I represent BITS Pilani along with my other BITS team members. I see a lot of familiar friends on the screen. I sincerely apologize for the lack of the video from my side. A technical glitch that we haven't been able to resolve. Hopefully during the course of the thing, I'll be able to do that. The whole exercise, the connect and the collaboration with Sintef and Trondheim and several Indian institutes and also European institutes spread over 4 projects now: ReFood, ReValue, IndiePlus, and EduCool. It has been wonderful. It has been a wonderful journey for me personally across 2 institutes, IIT Kharagpur and BITS Pilani, and many of you have become warm family members, warm friends for a long time now. I'll just spend a minute on this. I know the first speaker, Dr. Maitri Thakur, I'll introduce her. She will be talking about ReValue in a summarized high-level summary. So we were talking about 4 packages in work packages, 5 actually, and today. So we have had several meetings, and unfortunately, those were much more enjoyable in-person format, unlike today's. But then you make the most of it. You just don't keep on blaming the situation, and we try to make the most of it. And so today we are focusing. So we have had, we do have people from various disciplines of engineering, maybe dominantly mechanical engineering, and then we also have a large group, strong presence, footprint of life science experts, biological sciences, and today we are probably focusing more on the cold chain and the value chain and the supply chain, those aspects, maybe the refrigeration aspects, maybe the supply chain aspects in this. So we have had meetings, as I said, in physical format in Trondheim, multiple visits and meetings, and a lot of learning from those, very enriching experience for many of us from India, and also meetings in Mumbai, in Goa campus of BITS Pilani. Amity hosted a meeting in Kolkata. We all loved it, and all of us participated and coordinated and did things for all these meetings to make it a success. One of the unique feature of this collaboration, the research collaboration, has been the participation and active participation and collaborators from the industry, relevant industry. That has been the case, and we'll probably mention that in course of all the presentations. Without spending any more time, let me quickly go over. I'll come in between. I have the pleasure of doing the threading across all the speakers. I'll come in between and introduce the speakers very briefly in the interest of time. So first speaker, Dr. Maitri Thakur. She's the boss of this project for all of us in a very sweet and warm way. We loved it throughout. She is a senior research scientist in the climate and environment department at Sintef Ocean, one of the major partners of this project from Norway. Received her PhD with double majors in agri-engineering and industrial engineering in 2010 from Iowa State University. Of course, as I said, she is the coordinator of this ReValue project. Research focuses on food supply chain management, food systems analysis, traceability, and information management. Maitri's background also includes valuable experience from managing and working in interdisciplinary consortia in both European Union and Research Council of Norway funded projects, NRC. RCN. Yeah, her research has led to several scientific publications and presentations in international conferences. So over to you, Maitri. Welcome. You are the torch bearer, so you will start this webinar, this conference. So thank you so much. I'll come back to you I request every speaker. Maitri will speak for about 10 minutes. we do not have a Q&A option in this one, but everything else we'll have. Okay, go ahead, Mike.
Thank you, Professor. It's really nice to see so many of you here. As he said, I'll just give a very brief overview of the ReValue project, which focuses on improving resource utilization in fish value chains. So ReValue project started in 2018, and we are just in the final phases now. The primary objective has been to contribute to the Sustainable Development Goal on food loss reduction by developing innovative technologies, focusing mainly on the surimi industry. This is the innovation project, which was funded by the Indigo, Eranet Bioeconomy. A budget of about 800,000 euros, which is jointly funded by the Research Council of Norway, Department of Biotechnology in India, and CDTI Spain. The project is coordinated by Sintef Ocean, and of course our partners include BITS Pilani and MIT University from India. We have Carensa from Spain, and we have had industry stakeholders involved from India as well, from the surimi sector. So if you do not know what surimi is, it's basically a minced fish paste. The second picture you see here, the kind of this white block, this is a frozen surimi block. About 3% of the world's fisheries supplies actually go into production of surimi-based products. And the surimi industry worldwide is responsible for approximately 3.5% of fish losses. But there's high protein content in the coast streams or rest raw materials, as we call them. So they're very valuable from the nutritional, environmental, as well as socioeconomic point of view. So we need to take care of these rest raw materials in the best way possible. This was the plan for the ReValue project. It's divided into 4 research and innovation work packages. The focus of today's webinar is mostly on cold chain management, which was work package 1 in ReValue. We also have some external speakers you will hear from. And then we also looked at different valorization techniques and application of the ingredients that are derived from the rest raw materials of surimi production, as well as market exploitation and economic evaluation of the processes developed. We have several exploitable results from the project. And since this was an innovation project, the focus was on developing technologies at a higher TRL, or at least demonstrating them, so the results are above TRL 5 at least. So the key results focus on climate-friendly refrigeration, which you will hear about a little bit later. Improvement in cold chain, as I mentioned earlier, processing of the rest raw materials. We have solid rest raw materials as well as wash water that's obtained from the surimi processing. So how to utilize this further for making food and feed ingredients has also been the focus of this project. Some results so far. BITS Pilani led the mapping of the supply side of the surimi chain in India. So that they've done a really good job with that to kind of understand how the supply chain looks like, what are the challenges related to cold chain management. And then they've worked also jointly in the project on designing climate-friendly refrigeration systems. We'll hear later from Professor Dasgupta in his presentation. He'll go over the details of this. They've also been working on extraction of ingredients for food and feed applications. And we will have a second webinar in August that focuses on the valorization techniques. We've published a lot, we've presented in many international conferences. Here you see some examples of reports and scientific articles from this project. Very happy to say we have 4 very dedicated PhD students from India who have been working on the project. So the project has also contributed to the education of, yes, 4 PhDs. That's really good. I think I will stop here. I just wanted to give you a very brief overview, and we'll go into the details of the research in the next few presentations. Thank you so much.
Thank you. Thank you, Maitri. You make the job of this, timekeeper so easy. So I'm going to have a bit of cushion because of your early closer. Thank you so much. With that overview, lovely photograph on the screen of all of us. This was taken in. Can't remember.
It was the last physical meeting in Trondheim.
And so that I move on. The next speaker, dear friend from Norway, Professor Armin Hefner. I had the good fortune of talking to people from his lab and visiting his wonderful laboratory. He took me around. Thank you so much, Armin, for that. So let me introduce Armin on he's going to talk about advantage of natural working fluids in the global and Indian seafood cold chain, and probably in general food cold chain. So Armin received his doctoral degree in energy and process engineering from the Norwegian University of Science and Technology, NTNU, that's Trondheim, Norway. Currently a professor there of refrigeration engineering and technology, and his research addresses a very well-known, if you have ever read anything on CO2 as a refrigerant or transcritical CO2 systems and related things, he's a household name there. So you would know. His interest addresses the utilization of natural refrigerants such as carbon dioxide, CO2 for various applications in refrigeration, air conditioning, and heat pumps, system design, life cycle climate performance assessment, and so on and so forth. His research has led to over 150 international and national publications, numerous presentations in international and national meetings and conferences. So over to you, Armin. You do have, this is a very involved and substantial presentation. So Armin will speak for about 25 minutes, and we'll have some questions and answers after that. Over to you, Armin. Thank you.
Thank you, Sovik, for the nice introduction. Good afternoon to India, good morning else, and welcome to the presentation for today, as already mentioned by Professor Sovik. Today I will give you an introduction to refrigeration, where does it come from, and look at our journey from the Montreal Protocol via the Kyoto Protocol to the Kigali Amendment of the Montreal Agreement. So, and where do we go ahead? And the big question is, are there any sustainable synthetic refrigerants? And then I will show you some spearheading examples of real green cooling for seafood, but also other food, mainly related to food. And I will tell you what should be mandatory from the end user point of view, and how could smart loans accelerate the phase-in of natural working fluids for all cooling applications. So why do we have mechanical refrigeration? When did it start? Actually, before it was like this. In the northern part of the world, people were cutting blocks of ice in the lakes in the winter, and it was stored, and it was exported from Norway. More than 150 years ago, ice was the largest export product from Norway. It was even shipped towards England, but also then ahead to India to have the Scotch whiskey on the rocks. The rocks were actually from Norway. And it was also by that time introduced the export of frozen meat from Argentina, also food transport, cold chain already by that time. That's when mechanical refrigeration was introduced, but the driver was actually beer brewing. To be able to brew beer in Germany all year long, Carl Linde, he invented big refrigeration plants, and within a few years he sold more than 800 of these all across Europe. So beer production and food transport is actually the reason why we do have mechanical refrigeration and why it started in the late 19th century. So this is just it's a journey from the 1800s to 1930. Mainly natural working fluids were applied. There was nothing else. But then in the 1930s, there was a massive lobbying and the introduction of safe synthetic working fluids, mainly the CFCs and later the HCFCs. It was a success for the chemical industry, but as we all know, there was a challenge with the ozone layer. And the Montreal Protocol was globally ratified within 2 years. That is really congratulations to the world. This has never happened before. And since then, that such a global agreement has been ratified so quickly, but people understood it is urgent. And this triggered, of course, the introduction of HFCs, because they were promised as an alternative from the chemical companies. At the same time, actually, this initiated also the revival of CO2 and other natural working fluids by the former Gustav Lorentzen, professor of our institute. So it was the starting point of a revival. 10 years later, there was the Kyoto Protocol. It took measures on the global warming potential, but it took 7 years to ratify it. The US didn't join, China and India, they were not accepted to do any commitments. So Kyoto Protocol was not that successful in a way. It triggered some developments also in the food chain, in the food, some of the sellers of soft drinks and so on, they changed all their bottle coolers and so on, but it's not that the big stuff didn't come. Then we have in Europe the F-gas regulation, which is quite strict and has a phase down steps on GWP, the global warming potential of the working fluids. Similar things were implemented in the Paris Agreement, and we had in 2016 the Kigali Amendment, where also India is part. And again, we see that this is a massive lobbying now, pushing some other ultra-low GWP fluids from the chemical industry. But the big question is really, is this F-gas churning to the best for society and the environment, or to the best to some few people? So that's the big question. And I think the answer is actually simple. And are they really sustainable working fluids? That's the question. Let's have a look. Our friends from America, they did an intensive screening and survey to find suitable refrigerants. They used a chemical database. They studied 60 million chemical combinations to find out which combinations can be applied in refrigeration systems. And they excluded some which had a very low COP, coefficient of performance, or a volumetric capacity. So those were excluded. But at the end, they came up with a list of 27 fluids. So that's the toolbox now. And they have also hydrocarbons, the old HFCs, which are on the phase-out list because of the global warming, some new so-called HFOs, but they are also HFCs, CO2, ammonia, and some others with oxygen, nitrogen, and sulfur. So, but the big conclusion was there are no fundamental new classes of chemicals available. So what's on the list now? That's it. That's very important to understand. So, you cannot continue and say, there will be something coming in 5 years from now. I don't need to do any investment. Then you're on the wrong direction. But the second conclusion is even more strong. You as a manufacturer of this equipment, you would like to have a drop-in. Do as little as necessary to replace the fluid and go ahead. But this is not possible because the properties of these fluids are different. They're generally very different. So you need to adapt and to change your systems anyhow. Otherwise, you compromise on safety, efficiency, reliability, and that you don't like. So you must spend effort to change your equipment. What does it mean? Yeah, but then, okay, I use this new so-called ultra-low GWP fluids. So let's have a look on this toolbox. When we look at the propene kind of possibility, see, this is how the propene looks like. It has this double bond, three atoms, carbon atoms, and the rest is are the H1s. So this is the possibility. If you replace the hydrogen with the chlorine, you get this combination. At the end, you have a hexachlorine propylene up in there. Or if you replace the hydrogen with the fluorine, you go in this direction. So what do we see here? This, and then, sorry for the small sign, but here you find them 1, 2, 3, 4. You find all of them. This 1, 2, 52. This is the nomenclature we use in refrigeration. So, but what do we see here? Oh, happen here. These are the stuff which was ozone depleting. We don't want to go back there. We don't want to have that blackjack card again and be responsible for the next problem. So these are not an option. But okay, that's why the chemical companies say, okay, look, this we have ultra low GWP. This stuff is very short lifetime in atmosphere. That's why the GWP value is low. But are these really options? Let's have a look. This stuff is in all new cars. If you buy a new car on the global market, most of them have this. So it transforms to HF and TFA. Is it healthy? No. The other one, this one is another alternative, heavily supported in chillers, air conditioning systems, and both are kind of blend ingredients for new blends. And what happened with them? There's an Australian guy, he's a scientist, he's good. He discovered that there are different kind of degradation channels, not only the one which has been kind of released so far, there are others. Because the problem with this fluid is it is degrading into something which is this one. And you don't need to be a chemist, but you must understand what happens. So there are different kind of degradation channels, and then the energy from the sun and so on breaks up these molecules again, these intermediate breakdown products. But what happened is that there is a significant amount of R23 produced out of this. But this product has more or less no GWP, no global warming potential per definition. But when it is released into the atmosphere, it creates R23, which is our worst case, which has 14,000 kilograms CO2 per kilogram fluid. So this is not good. So how can we claim that this is an alternative? And this puts the spotlight straight to the point. Our definition of global warming potential is just based on what's in the bottle. That is like this one. Yeah, I have a low GWP value. I don't care how much energy and other side products I have doing manufacturing. That's not in my account. And I don't care what happens afterwards. That's not my business. How can we in 2021 think like that and make legislation according to this? We should know better. So that's why if you are focusing on natural working fluid, that's really sustainable, because you and your customer, you will face no risk that your technology and products will be on the phase out again very soon. Because what I just previously showed, this finally it will be understood by the politicians and society that these are no alternatives. They are just making money. And we need a safe and sustainable investment. And that we can do with fluids we already know and how they perform. Just show you an example. Supermarket, that's the final part of your food chain. We see a lot of CO2 supermarkets coming up all over the world, replacing all the HFCs. And I show even some examples later where how this can be done in regions with warm climate. We even see for car air conditioning, I showed you before that the one stuff which is inside in all cars now, there are some developments. They're using CO2 now. Actually in Volkswagen, the new ID cars can be equipped with this kind of heat pump systems, because the electric car in the winter, if you need to heat up the car, it needs this, and then you will find this sign, R744, that's CO2 inside the car. I will talk about food and fish processing at very low temperature, which is possible with CO2. I will show you some examples on a heat pump chiller, which is relevant. We know that there are many commercial units with propane in the market, in all different categories, in the shops where you sell food and all this. This is a well-proven product, and it is very sustainable. Even you can, in India, you can buy split air conditioning units for your home with R290 if you are thinking ahead and do that choice. We can also do low charge ammonia chillers for cold storage and all this. So let's see. This is an example of a supermarket done a few years back in Portugal in a warm place. In this machine room, you see the nice unit. It has all integration what you need. You have the low temperature for freezing part. You have the medium temperature for the chilled food cabinets and cold rooms. We do also air conditioning and humidification and even heating in the winter period. All is done only with CO2. And this shop owner, they can register that they have a saving of about 30,000 euro a year compared to the previous installation they had for all their shops, which was a cascaded system, CO2 and HFC, but the integrated one is much more energy efficient and it saves a lot of operating costs. Similar, you can see in Jordan, which is also a warm place. And look, they did leapfrog from what you are using, Gary, R22, straight to CO2, also 3 years back. This saves a lot of energy for the end user. And even the 20 kilo of R22 they normally needed every year to refill is also not necessary anymore. And this system has been in operation since 2018. There was no problem, no breakdown of the system. The owner is so happy. They have not lost any food and they save a lot of energy. Yeah, and I will come back how we can get more of these units into the regions, because the challenge is still the investment cost, but you can see the operating savings are there. So we need to find a measure to overcome this problem with the slightly higher investment cost. On the right-hand side, you see a simple schematic of the system where we see how the different parts are connected, what kind of components we do have. If you would like to read more about it, there is a nice paper presented at the ICR in 2019, or get in touch with me. Later on, I can help you to find these documents. Another example is a heat pump chiller, where we can utilize the cold part for your production lines. It doesn't need to be 12/7, it can be also for chilling or even below 0 degree ambient products for the processing in the food process industry. At the same time, you can also produce 90-degree water, which you can use in your zip lines to disinfection, cleaning purpose, and all this. So, and the unique innovation here is that we utilize an ejector which recovers some of the expansion work which we do have when we have a refrigeration system where the compressor is compressing the gas. The heat rejection devices are either utilizing the heat or we reject the heat to the ambient. And then a small internal heat exchanger, we come to the expansion device, maintaining the high side pressure on this level, done by the ejector. And instead of just flashing down, we are utilizing part of this work to suck at the lower pressure level from an evaporator into a separator where the pressure is taken care or is the pressure level of the compressor. So this pressure is lower than what is the pressure here, and that's why we can generate more cooling capacity at the elevated suction of the compressor, which is beneficial for the efficiency. And actually such a unit is currently built in India. It is built in the southern part of India. We have another joint venture. We are working together with different companies, and this unit is producing hot water from 24 to 90 degrees, while it is chilling other water from 12 to 5. And we expect the performance ratio about 6.2. That means for every kilowatt hour we put in, we get 6.2 on the other side. And this is a nice cooperation, and this heat pump will be placed at the Askaya Patra Foundation. They are doing these school kitchens to deliver food for school children which cannot afford to have a daily meal. So there are around 2 million children in India getting daily food from this foundation, which is really good. And they have one of the kitchens is in Bangalore, and there this unit made in India with the support from European companies. They're sponsoring the components, and we will see how this unit can perform in India, and it can be taken ahead to all the production facilities where they cook the food. And if, of course, this company, the company building it, they can also sell it to others. So this will be hopefully finished when the COVID is a bit lower by the end of this year. Then we can report from it. Transport refrigeration is part of the cold chain, and you see there are CO2 containers operated with CO2 as a refrigerant. So there are possibilities for that part of the cold chain as well to have a sustainable refrigerant globally. And now to seafood, we have a close cooperation with the PTG in Norway. It's the Perfect Temperature Group, and together with them we have leapfrogged our industry, our seafood industry, from R22 straight to CO2. 10 years ago, the first developments were done to produce a refrigerated seawater unit for on board of a ship. Of course, the prototype was heavy and expensive, but still this unit is operating west of Africa today. And nowadays, this company has delivered more than 50 of these units towards many boats in Norway. So the product today is from a very small one, maybe 50 kilowatt, to produce refrigerated seawater. They can have units up to 500 or 450 kilowatts. But what you can see, these units are rather compact. So this is very compact because it has to be fit into a ship. So space is limited, but it has been shown before that when you replace the R22 system, you can actually install more capacity with the CO2 system because the system is more compact. And that's what the owner likes. And this can cope with seawater, of course. It is a little bit enhanced with an ejector, a very successful product. And this should be possible to also be produced in India. They also we're doing freezing of fish on board in Norway, and CO2 is able to provide freezing at -50, which gives you a 25% faster freezing process. So your quality of the fish will be better because it goes much faster to freeze a catch. And you see these kind of units, they can do up to 60 tons a day. And they are designed for -50. It's pump circulated, and even the defrost out of these freezers is very fast, and the surface is not getting too hot, so the quality is preserved of the fish, even the one which is on the outside, which faces the defrost or the hot gas or the warm gas when to release the block. Very successful product, and again you see how compact these units are to be placed on ships. But what is important now for the end user? The key factor for this fast phase-in of a real green natural working fluid is the training and knowledge and the understanding of the end user and you that we cannot do green cooling just by greenwashing a number and say it's a low global warming potential. It has so many other byproducts which are not inside that number. So we know if you use natural working fluids, we can do it. And important is that the end user is aware of what he really becomes responsible for. He must be aware of what is in the material safety data sheet of that working fluid. He will see that sign there, but maybe not all of the suppliers are telling them what is actually in the system. And the end user must ask about the seasonal energy demand and the total global warming potential, the total impact of the fluid, not only just this, what's in the bottle. That's very important. And from now on, this is very important because they don't want to be cheated. If they hear in 2 years that your system has been using such an old fluid, which is not at all sustainable, do you think they will come back to you? Not sure. So what is important that all the vital cooling devices can be made available, energy and cost efficient, and environmental benign with natural working fluids. There is no need for HFCs. And why should you do a detour from your HCFCs to something HFCs and then thinking about natural working fluid? This is waste of resources. You should go straight to natural working fluid because then you have a solution which you can even sell and maintain in 20 years from now or even beyond. And if you have to go to a flammable working fluid like hydrocarbon, it's not a problem at all. It works very well if you follow the norms and standards, because most of these new HFOs, they are all flammable. So you have to go into these flammable guidelines anyhow. But it must become and requested by the end user that all the environmental impacts are shown, are made public, and this must be mandatory from the supplier. So they must do this. And if they can't, they should not be allowed to sell this product. And the question was, how can we accelerate the phase-in? Look at the example from Jordan and other places. It should be so easy that the World Bank, multilateral funds, your national governments and funding programs, they should support end users to cover the additional first cost of the cooling unit, because that might be a slightly higher. But if they could pass an affordable loan which follows the unit, then the operator, the end user, he can return that during the operational phase, because as I showed you, there is so much saving on the operational costs. So this should be for the governments and this World Bank and so on. This should be the mantra, what they focus on in the near future. So thanks for your attention, and of course I'm happy to answer your questions.
Thank you, Armin. As always, lovely presentation, deep thoughts and analysis. I don't see anything in the chat box. We can take a few questions. Is there any question I hope I'm reading the right chat box. It's empty. If anybody else is able to read questions, please go ahead and speak. Or you can, I don't know if people can unmute themselves. Armin, are you able to see anything? I see, okay, there's a comment.
Now it's coming in, yes.
Yeah,
thanks.
Coming. There's a comment from Aftab. Yeah, thank you, Aftab, for that. Yeah.
Yes, any question? What a summary. What does it mean? What a summary?
Yeah.
The summary is you saw here, right? And you find the presentation, I think you can, if you need this presentation or something from it, send me an email and I will be happy to provide it to you.
That's the email address, armin.hafner@ntnu.no. Yeah, and I think on our ReValue site, we probably will be hosting some of the presentations. Yeah, most likely. We'll see PDF versions, of course. Yeah, so people are appreciative, but not really asking questions. I mean,
I want to know, are there any more published results to becomes like, yes, you can, I gave you some of the links here. Let me see. Sorry.
Yeah.
I can send you, if you follow these here, you find many information. And it's towards R23, 22, no, but it's 23, and that is worst case. And Mr. Hansen, he's found it's about 10%. So 10% of 14,000 is 1,400.
I mean,
these should be added to the GWP value, but not taking care of all the energy which is used to produce it. So that comes up front. And this R23 is one stuff, and the other 90% is also not harmless.
So I have a sort of a generic thought, maybe a question. It can be shaped into a question for you to just. So you know, these synthetic refrigerants, at the time they are invented, and so normally we don't have, once it is marketed, obviously we don't have at that point of time revealed drawbacks, you know, damages that it can cause, because the way the research stands at that point of time. But decades later, we discover, unfortunately and disappointingly, that it has been causing problems since the day we introduced it. But that was much later, maybe 20 years or whatever, and the damage is done. You can't roll back those 20 years. So isn't it as a principled stand that we look at NatRef and not go into synthetic refrigerants, because you are dependent on the quality and depth of your ability of your research. It may not reveal it today, it will reveal day after tomorrow. You know, is
exactly that, but if we have a focus on this working fluid and the real focus, what is really inside, you will find always this trouble as long as you have a synthetic fluid. If you're working and developing natural working fluids, you can focus on your development. But I would like to answer some of the questions. There was a question if there is a governmental support. Yeah, we do have some other project. It's called Indy Plus with the same people. BITS Pilani, others are involved. I can share also. I shared in one of the slides the website. We do some efforts there. We help to develop these systems. But the good story is, you don't need governmental support. If you do this development, you will earn money from day one. It will be a very easy investment if you really focus on this. Next question was, there is for the -5 plate freezers. Yes, that will be also demonstrated. And how can CO2 cool faster? Yeah, with the previous system, you couldn't go to -50. A plate freezer needs temperature difference to be fast. We are not talking about COP. It is more the production, the quality, the money the fisherman can earn. And then if he has a system able to operate at -50, the plate freezers are much faster. This gives him more profit. That you can do with CO2. Small capacity, of course, it's challenging, but Maybe you can do that with hydrocarbon system for small applications. It's not a problem.
Right.
It depends.
We may not be able to take all the questions because we have to watch the time. So maybe let's take this last one. Do you know what's the payback period roughly for these CO2 technology against conventional systems in Asia for seafood application? This one is the last one.
I think there is no difference in the real payback, because if you implement all the costs also for society and all this, you will see that the end user, he gets a much better product. It can last much longer. So if you take the total cost, I think we are quite close.
Sure.
But we help you to develop these kind of units. And if you have questions, please contact us.
Yeah,
Thanks.
Please contact. Please write to Armin. Thanks, Armin. There are
ammonia is good too.
partners.
Ammonia is also nice. I see that.
That's right. Yeah, we'll talk about that. As Armin mentioned, there are other partners in some of the other projects we have connected with. There is IIC Bangalore, there is IIT Madras, and of course NTNU is always there, and SINTEF. Thank you, Armin. As always, loved it. And let me move on. Building tomorrow's sustainable fisheries value chain. That's the presentation that we will have now from the president of Danfoss Industries India, Mr. Ravichandran Purushothaman. So Ravi, I will address him as Ravi. In over 32 years, he has held roles spanning across sales and distribution, business development, project management, change management, and general management functions in India and Asia Pacific regions as well. He's an electronics and communication engineer who completed his management education program from IIM Ahmedabad, has participated in strategic leadership and international business programs in European business schools. He's also one of the key members of the CII, Confederation of Indian Industries, CII National Task Force on Cold Chain Development, and has been an integral part of CII committees, which focus on education, energy, and green building. So a man in the zone, I must say, and is the leadership in one of the most well-known companies in this area of business, Danfoss. So Ravi, over to you. You will have 20 minutes of, I request you to stick to time, and so that we can also have Q&A at the end. Over to you, Ravi.
Thank you very much, Professor Suvik. I hope I'm audible.
Yes, you are.
Okay, and you can also see my screen, right?
Absolutely, yeah, go ahead.
Thank you very much. So the first disclaimer is that, I'm a communication engineer. I'm neither a refrigeration expert nor, refrigeration and air conditioning expert. But I will try and give you the perspective of where I'm sitting and looking at India. And if we need to build the next billion-dollar industries in India, surely fisheries is one of them, actually. So I have to thank Professor Suvik, also Professor Pramod from Indian Institute of Science, and my colleagues Manyam and Krishna, who have helped me put together some of these thoughts as well, with whom I've been working for a long period of time on this. So let me jump in today into what I'm going to talk about in terms of value chain. I think I would be covering a little bit about where is India stuck in terms of the world picture, in terms of what are we doing and what is the outlook for us? What are the current opportunities and challenges that we see in India? And how do we shape this industry and kind of put a vision around how do we build an industry that is far more sustainable, but at the same time creates a great opportunity for making India a $5 trillion economy, and at the same time meet the several sustainable development goals, which is another fascinating opportunity this industry offers. And then I will deep dive a little bit into what I think Professor Armin led me into, the talk about why I personally believe ammonia CO2 combination is the most sustainable model for the future in India, and then kind of leave with some conclusions, actually. So when you look into when you look into the big perspective on the world map, I think sometime in the mid 80s, you started to see the fish that was hunted on the ocean started saturating. And I think aquaculture started becoming a very important part of the fish industry. Clearly, when you look at opportunities, we have great opportunities in both the areas. On one end, fishing on sea needs to be even more sustainable, where there's a lot of opportunities to do electrify the vessels, put CO2 on board, and many other opportunities are there, which is one part of the story that we have to look at in the future. But clearly, I think the message that I want to leave you all with is that there is a very strong increase in aquaculture, and it has kind of kept growing, and it is also expected to grow in the next decade. So this is something which is important to notice. When you look at this, why I believe fisheries and sustainable development goals have a very direct connection. And when you look at the pie chart, clearly, I think I've sliced the Asia-Oceania region. And when you look at the Asia-Oceania region, India is going to play a very critical part here. Now, let's understand, India is the second biggest producer of aqua and fish. We are the fourth largest seafood exporter. Today, we export to almost 115 countries, actually. And we produce almost 6.5% of the world's fish production. And fishery as a sector, we have roughly about 20 million people directly employed and about another 20-25 million people indirectly employed. So it's a kind of a 50 million, people involved in this industry, actually. When you look at the opportunity that this industry presents for India, on one side, while we have great opportunities to grow the aquaculture, but I think the sustainability element on what we do today in the sea catch, as well as the futuristic sustainable requirements on the aquaculture is really needed to be looked into and recrafted and reimagined. I think from an opportunity point of view, the consumption is growing. The production is also growing at a faster pace. And with all that we have in front of us, I think the demand is expected to be met only by aquaculture. And I believe truly that India has to look at how we can play a bigger role in the world market, like we have been doing extremely well on many other commodities, from mangoes to pomegranates. When you look at the Indian picture, we currently have about 25% post-harvest losses. And this is the full value chain. When you measure it, it's like there are many papers. In some papers, it is more than 25%. In some papers, it's about 23%. So we have about 25% post-harvest losses today. When you look around the ambitious plan the government of India has laid out, even though we have had a decline last year of about 10% due to the pandemic, if I have to look at what the MPDA chairman, Mr. K.S. Srinivas, says, the aquaculture sector has performed better than this fiscal by contributing to almost 70% of the exports in dollar terms and about 46% in terms of quantity, actually. So this is still a very big growing industry. And it's also a big livelihood provider in the coastal part of India. And I think there is a lot of focus by the government to double the income or double the exports to 1 lakh crores. And I think when India is putting the focus on the $5 trillion economy, very clearly this is one big industry that can be a big game changer for India. We need to craft it rightly, and actually we need to make sure that we not only look at the sustainability element, but also we need to look at how do we become an exporter of good quality, using the right practices and using the digital opportunity that India has in terms of its traceability. So a lot more needs to be done in this area, and that's also what my presentation is going to cover a little bit about. Moving in a little bit into the different processes or steps that we go through in both inshore fishing and ocean fishing. I think we actually have different phases in these two elements, but the criticality is that we need to maintain temperature right through the value chain, and that's very, very important actually. And potentially here I see there are three important areas where this temperature requirement comes to about -50 degrees. And these three important areas are very critical paths that we need to look at. How do we do it in a more sustainable manner? When you look at the current state in the industry, primarily this industry, as I mentioned, is very fragmented, very distributed. The processing centers are pretty much in the rural parts of India. And when I look at this industry, there are primarily current practices that are there, where we look at ice manufacturing as an important activity. And we have a number of refrigeration plants between 10 to 50 metric tons per day. We have quite a number of aqua processing plants where the temperature requirements are up to -40 degrees. And they are also spread across the length and breadth. The maximum sizes are between 10 and 100 metric tons per day. And the sea cache processing plants, which are the fishing harbors that we talk about, and those located close to the harbors, we kind of typically see plants between 10 to 200 tons per day. In all of these, what kind of applications we have seen is that we have seen plate, flake, and tube ice machines, blast freezers, and I think these have been traditionally the areas that we have observed as potential opportunities. Now, when we look at how do we build a sustainable model here, and here is where I come with CO2 as an opportunity. I mean, CO2 firstly is a non-toxic product. It's non-inflammable. It has very, very nice refrigeration properties. You can smell it. It's only 400 ppm. It has got some unique properties. Despite the pressures being very high, it gives you the biggest environment-friendly opportunity. And I think when you look around the other benefits that are lying with CO2, very clearly CO2 also helps you to get better cooling. I think you heard about what Dr. Aman said about the faster cooling opportunity. The footprint also becomes very, very small because you're handling, the piping requirements are small compared to ammonia. Even though it's small, I think the requirement there is probably a little bit higher skill. Product quality gets better with CO2. So there are a lot of arguments very clearly towards moving to CO2. And we did a small case study, which I would like to share with you here. A typical plant which requires currently ammonia, 100 tons per day kind of processing plant. If you move from a current ammonia system to a cascade system, which is on the plant end ammonia and on the processing side CO2, you can reduce the ammonia charge from about 20 kilos to about 2 kilos. I mean, that's the kind of reduction you can get on ammonia, and then you can have on the process side CO2 as well. So my recommendation is been always to my customers is to look for cascade system, combination of ammonia and CO2, because this is an extremely practical solution which helps us to meet the safety requirements, which helps us to meet the environment friendly. Because when you look at the gases that are available, propane, isobutane, and CO2, I think CO2 is a better choice. So there's no arguments in it. And of course, the total cost of ownership is another dimension that we need to remember, that because of the footprint sizes and probably the piping sizes are going to be different here. The number of stages of compressors that you need versus ammonia is still less. In a very typical 100 tons per day kind of plant, we have seen about 10 to 15% increase in the total cost of the capex. It's not a significant increase in my view, actually. And of course, given the fragmented nature of where India is sitting in terms of its footprint, I think this combination gives you a great opportunity. Now, what is the problem we see on ground? And before that, let me just tell you the advantages also. This is something which I think Dr. Aman mentioned. When you look at this picture on your right side, primarily, as you can see here, CO2 gives you very high efficiency and occupies lesser real estate as well. It also helps in rapid freezing and thawing, which improves the quality of fish. You can see the circle there, which is mentioned 40 degrees, minus 40 degrees. And while the one does not appear very good looking, but my friends who eat fish tell me that this has got a better texture, better quality, and better taste for consumption. And on the left side, there was a question in the Q&A box earlier, actually. The graph gives you an indication how much better CO2 is from an efficiency of rapid freezing. I think chill kill is a very good property which keeps the quality of the fish. Because finally, you know, when you reach it to the consumer, your pricing power comes from the quality and the repeatability of quality, I think. And that's where the brand part of it comes, where the consumerism gets a better opportunity for pricing as well. So in my learnings the last many years working in the industry, my own recommendation for building the full value chain has been always with ammonia and CO2. It has both have had a very good properties, and a combination of this, I think to my knowledge, when I look at the opportunity that India has, and with the ambition that India wants to double in terms of the value and quadruple in terms of the production, ammonia combined with CO2 is a great opportunity. Everything is ready in my view. We have all the tools. In fact, we have worked with several universities, both in terms of transcritical as well as subcritical applications. And we have seen that the seafood industry needs primarily subcritical applications. I don't see any need. We have everything that is needed to really get on to start. But I think what is missing in India, to my knowledge, is the mindset. And I think we still are very old-fashioned in designing projects because of this big safety challenge that we see. But I believe truly that the mindset can be only overcome if we have very strong policy intervention by the government. And I think the government should really stop giving, subsidies for or promote more subsidies for CO2-based applications. And that will help us to meet our vision for a more sustainable value chain. And I think given the fragmented scale India has in the 9 or 12 clusters where fish is grown both in aqua as well as in sea catching, I clearly see CO2 is more attractive and more sustainable. I think we all need to work together to build a very strong ecosystem, and I truly believe this is achievable, and all we can do is to leave a better planet for our next generation. I think that was a short update from my side. I'm happy to take some questions if there are there, Professor.
Thank you, Ravi. So we wanted to have speakers from various sectors, from the academia, from the R&D labs, and from the industry. So Ravi represented the industry from India. We will have another speaker, another Ravi actually, Ravi Pati later from the USA. And yeah, so question time. Let me see the chat box. I don't think there is any. Thank you, Ravi, for a very enlightening talk on this. And, while we are waiting for some questions to be coming in the chat box, I request the delegates as well as the speakers, whoever is willing to join the team and the research efforts that we are, giving in terms of various initiatives. This project, ReValue, is coming to an end gradually. And but other initiatives with many of us are there in this. So please come and join and work with us. Invite you to interact with us. Any of us can be approached, send an email, send a message, and we'll be happy to take it forward. So let me see. I don't think I have anything and in the chat box unless somebody else is seeing. Okay, so one of the questions that came to our mind, Ravi, while we were interacting with the user meaning the people who catch fish and freeze and so on, and then they export. Of course, there are nagging challenges because in India you cannot have everything tailor-made for you. We found that huge gaps, huge complex socio-economic, even political challenges. Who will bring it to the truck? Who will drive the truck? Who will cool it, and so on? If you are the best, you are not allowed to do that. That sort of thing is there, but I don't know if in terms of the cold chain. If there are technical issues, of course, many of them we have heard already, but then there are non-technical issues. I mean, can you throw some light that what's the best way about going about this supply chain, this cold chain thing? Because there are breaks, there are cracks in these gaps, which actually fatal, which are actually dangerous for the product. And you end up not able to export because of quality issues, because of texture issues, because there are moments and minutes when the product or the fish was not under the right temperature. It was warmer than that, and so on. So can you throw some light while we wait for a question, maybe?
So, Professor, I think there are two elements to the challenge that we have. We have an economic challenge, which is more around the sustainability part on how we manage the whole value chain, how we create value and how we capture value. That's one element of the problem we have. And that's where we talk about technology, the right models and all of that stuff. We have a bigger social problem. I'll give you a few examples where we have struggled a bit actually. When you look at fishery, there are three buckets: the pre-harvest part, the post-harvest part, and then the last mile connectivity part actually. In the pre-harvest part, especially when we talk about fishermen going on the boats to catch, ice is a big political subject. When you go into a fishing harbor, how ice is produced, the quality of ice is a big political subject. You go with the best of the technologies and say, here is an ice flake machine, which is more environment friendly. You can reduce your losses by 18%. Just use this technology. And you probably need only electricity, but we also have a solar option, and all of that you provide. It doesn't fly because it's a political challenge there on ground. Because the guy who actually makes the ice, he belongs to one political party. It is his bread and butter every day, morning and evening. So this is a very so basically we need to look at how do we engage with the communities. So it has to be a community driven PPP model, if you want to bring transformation there. And sometimes we have seen successes in the agriculture field that when you bring new skills to the farmers and kind of society, you need to bring like-minded people first and transfer the knowledge. And then these farmers should go and talk to the other farmers. If industry try and tell something, it doesn't work. So this has been working very well for us actually. The second challenge that we see is, we need to treat our fishing harbors also with little respect. I mean, we have not invested in creating world-class fishing harbors. Only in the recent budget, we have seen that, 2 fishing harbors, I think they have identified for building up, because a lot can happen in the fishing harbor. Because, if you can actually put the right technology on the boat, you can even electrify these vessels because they don't go too far. They're only going for 4-5 hours or 6 hours. You can put the right technology. CO2 will actually reduce the dead weight of the boat. It can give you better density. It can give you faster cooling on the boat. So there's a lot of good arguments. And in fact, some of the shipyards have already started building the electric vessels already, but they are 1 or 2 in number. But we need to run these pilots and get early wins so that we can actually transform the catch, because that is where quite a bit of loss is happening as well in the early part of it. So in my view, I think a lot of social connect is needed in order to make this transformation. That's very important. Second, I think the political will is needed if we want to make a change in this industry. And that is a challenge sometimes I see. So this industry has great opportunities. And mind you, when we talk about this industry, it's a coastal livelihood, and when you look at how we can double, triple farmers' income, this is something very important,
Right. Yeah. I think this conversation with policymakers and the movers and shakers of those zones are important. And who knows, I mean, tomorrow we should have project partners who are actually well-meaning, well, if there is any, well-meaning politicians, Yeah. So that has to be that has to be one of the agenda items, maybe tomorrow. Otherwise, our efforts will remain within the laboratories, within the journal covers and the conference audiences. Yeah, it is not going to be translated on ground. So the industry is a good introduction, but we need others as well. I don't have a question in the chat box, but if anybody, any of the speakers have a question for Ravi.
I think even fish has got two different families, right? You have an economical category of fish, which is the tuna, the salmons, and the shrimps. And there are also socially important fishes like the hilsa in Bangladesh and the mackerel in Thailand.
Well, you tell me you are talking to a Bengali now. I happen to be a Bengali, so I know the value chain there. So, all right. You're absolutely right, and yeah, some of them are very seasonal, and some of them are sold at extremely high prices because of the exclusive taste and flavor, and so on and so forth. I think I'll close it here. Ravi, thank you so much. I hope that we remain in touch, all of us, the entire project team, and we continue this conversation so that we do something substantial in the near future. And let us make it a point, and if you have some immediate thoughts, please share, please text us, please write to us, and we'll do likewise. Yeah.
Absolutely. Thank you very much for having me here.
Thank you, Ravi. Wonderful. We move on. We will hear on refrigeration in the seafood cold chain. Now, there are people, long-time collaborators and friends, as I said. They've become like family members, really. And so Dr. Christina in Wedel, I have a huge pleasure in welcoming. Well, she's an engineer, of course. We were talking about, Ravi said that he's a communications person, electronics communications. So Christina works in of course, let me formally, she works in Sintef Ocean, Trondheim, Norway. She's a senior research scientist there. Sintef Ocean, of course, I believe it started within NTNU quite some time back, and now it has become a very important presence globally, not just in Norway, the huge research institute. And she works there as a senior research scientist in the Department of Fisheries and New Biomarine Industry. Primary areas are processing technology, systems and systems for food industry. Especially related to refrigeration, of course. Examples of activities of Christina in the areas of improving fish product quality, increasing process energy efficiency. As an engineer, many of us, we look at that, increasing the share of NATREFs, natural refrigerants, and reducing food waste. I think we have visited Trondheim and interacted with Christina. Of course, she has visited India so many times in many of our interactions. A wonderful engineering brain and analytical brain, and I have always enriching conversations with her on every opportunity. We will hear from Christina, Dr. Christina and Vijay. Christina will have 15 minutes for you, and of course after that Q&A. Over to you. Thank you.
Thank you very much for the introduction, and also thank you for the opportunity to have a presentation at this webinar. Just a short comment to the previous speaker that I think many of the things that he addresses is also some things that we will do within the new the project Indie Plus. So I hope that you will be able to kind of join the webinars in that also. I think it will be open. I will mainly talk about how things are in Norway, and many things are similar in other countries as well, but with different types of fish and different methods and somewhat different technologies as well. So in Norway, we divide the seafood into 4 main groups, which you can see here. It's the pelagic fish, which is mainly mackerel, herring, and blue whiting. It's fish from aquaculture, mainly salmon. Demersal fish or whitefish, which is mainly cod, saithe, and haddock. And then we have other seafood. Here you can see the production from each of these groups, and the other seafood group is very small, and the whitefish demersal is 1/5, and pelagic and aquaculture produces about 2/5 each. And you see also here the total salmon production in 2019. You are probably all aware of the effect of the temperature on quality and shelf life, and this graph shows shelf life on the y-axis and temperature on the x-axis. So lower temperature will result in longer shelf life. And herring, you can see here, has a shorter shelf life than cod and salmon. So we all agree that good quality of food is important, and these factors give good quality. Low temperature, I've said, but also good treatment of the fish is important. And for example, if mackerel gets too much pressure in the trawl, or if the salmon is stressed, this will be negative for the quality. And because the fish is perishable, it is necessary to chill it and keep it chilled also. The time is, of course, also important, and efficient processing, including good management. We often talk about cold chain, and by that we mean a food value chain where refrigeration is present, and refrigeration is freezing, chilling, super chilling, can also be thawing, which I will come back to. And super chilling means reducing the temperature below the initial freezing point without freezing it in total. And the typical temperature for that is -2 or -3 degrees. And this is one way of depicting a cold chain, and it's applicable on most seafood cold chains in Norway, and we are mainly working with the processing part. I will now share some results from 2 of our recent projects on quality and shelf life. And the first one is on what we call refreshed fish, which is also called freeze chilling. And that is fish products which are both frozen and then later thawed industrially. Otherwise, the thawing is often made at the consumer. And this project is on whitefish, and the fish figure here shows an example of a cold chain for these processes. It's maybe a little bit too difficult to grasp, but we see in the beginning you have either just gutting and chilling on board. It's on the left-hand side here, or you have gutting, chilling, but also freezing on board. And then it's a little bit different on which way they select for further processing. Either it's thawed again before filleting, or it is frozen and thawed later industrially before reaching the consumer. So why is this a good procedure? And here are some examples of why it is. The availability of whitefish is seasonally dependent, and this can both extend product shelf life, but also the availability of the fish. And it's possible to reduce food waste with a more concentrated temperature control and so on. And it could be also an environmental friendly transport if you select transport by boat instead of transporting by airplane, for example. And the value might also be higher. Here are some results from a thawing test we have conducted. So we thawed a vacuum-packed fish, you see here in the photo, and we had different methods of thawing. And the graph shows relative change in weight, which means that 0 is no reduction in weight. And the difference is not that large, but it is notable that the weight loss was between 14 and 18% for all the cases. And the first weight, where you only stored it, thaw it in a refrigerated storeroom, had least weight loss. And this is another project where we also looked at freeze chilling, but this time on salmon. So in our lab, we did tests on salmon fillets, and the diagram here shows the different treatments of the fillets. Some were just chilled, and some were frozen and then thawed in different ways. And afterwards, it was stored in different temperatures. And we also did some analysis of you can see here the sensory analysis, drip loss, texture, microbiology, different days after it has been thawed. Here are some results. Again, quite a lot of information here, but we have not published this yet, but it will be published hopefully in not so long time. We can see here the different storing methods, and the x-axis is days of refrigeration for both the graphs. And we see that the chilled samples have the best scores for both sensory analysis and drip loss. And we have some unexpected results as well. For example, that thawing of a night at 4 degrees seems better than at 2 degrees, but we will need to have a look on that as well. Otherwise, it does not seem to be a large difference between fast and slow thawing. So this indicates maybe that chilling is a little bit better than freeze chilling, but we need to come back to that as well, because we froze the fish at -25. And as you heard before, maybe freezing at much lower will also increase the quality afterwards. So that is a potential for a further project. Okay, I will now talk a little bit more about the procedures in each of these seafood groups, focusing on the industrial processing stage of the cold chain. So pelagic fish can be caught close to land, but often it's caught far away from shore. So it could be 3 days from the Norwegian coast. And this photo shows blue whiting caught with a trawl. And this is fish that goes mainly to feed production and are seldom consumed directly. And the fish is pumped on board the ship, and it's necessary to do that quite fast. Otherwise, it's the risk of the trawl, the whole of the trawl sinking. And this is how it looks like inside the fishing vessels. They have large tanks, commonly between 200 and 300 cubic meters, and could have, for example, 9 of these. And before the fish is pumped on board, these tanks are filled with refrigerated seawater, RSV, which has a temperature of about -1 degrees. And this can then ensure fast chilling of the fish when it's pumped on board. We have several times participated in research cruises where we have conducted measurements, and I will show you some results from the last cruise. And the goal was to map energy flow related to onboard RSV and refrigeration systems. And we did energy measurements and flow and temperature measurements, fuel consumption measurements, etc. Here are some results. Here, this shows the timeline. The first period is when the vessel is steaming to the fishing ground, where also seawater is pre-chilled. And COP for this period is shown here. And this is the second part where the fish is chilled and the temperature of the fish is maintained. Here are some results. And so we saw that there is a high performance measured during pre-chilling and also initial chilling period. But then during a maintenance chilling, the performance is much lower, and this period is also normally longer, which results in an overall performance which is not that good. This is something that will be presented in a conference in Norway in September, so you may hear more about it there. Okay, so when the boat comes to land, the fish is pumped into the fish processing plant, where it first is stored in RSV tanks and then processed further. And in Norway, most of the mackerel is frozen in freezing tunnels and packed in boxes of 20 kilos and put into these freezing tunnels. And this is a freezing storage. And then we have the white fish, the mussel fish, and the onboard the fishing boats. It is often gutted and then refrigerated, either frozen in blocks or it's stored fresh on ice, or even the small boats may not have any refrigeration at all. This is a photo of a plate freezer, and the refrigerants are mainly ammonia, but we also see, as has been presented before, some CO2. On land, it's either exported or is processed further, and mainly chilling and freezing as refrigeration methods. The salmon is produced in farms along the coastline in these kind of sea cages, and then it's transported alive in well boats to holding cages which are next to the processing plant on land. And when it comes to from the holding cages, it's pumped into the processing plant where it's stunned and killed, and it will be then chilled in. This is an example of a chilling and bleeding tanks. And it has refrigerated seawater, and the fish is stored then for 1.5 hours before it's processed further. Here you can see before the fish comes into it, and this is how it looks after the fish has entered. So this is a small group, but I include it here because we had a quite interesting project where we transported live lobsters to the market in Europe. Normally they are transported dry, which results in some mortality and stress of the animals. And in our test, we transported the lobster in refrigerated seawater with very good results. So the vitality was high and mortality was low. And this is something that could be used for other seafoods as well. So just a brief summary. So in the fish processing chain, it's of course important with good fish quality, and that comes from low temperature, gentle handling, but efficient cold chain is also necessary. And there are many other related aspects which you have already heard, and you will probably hear later in other presentations as well. So it's reducing food losses, energy efficient processing and reducing emissions, sustainable resource utilization, and climate and environmentally friendly refrigerants, as Armin was talking about. And all these things are kind of important in what we do and what our projects. And I will also take the opportunity to inform you about the next year's Gustav Lorentzen conference, which is on natural refrigerants, and it will be held in Trondheim in June. Like now, it's a really nice time of the year, and you are very welcome, and I hope you have the possibility to come. Thank you very much.
Thank you, Christina. Good to know that you are doing the GL 2022 over there. Yeah, hope to join. Thank you. Do I have questions? I probably don't. Is there any question from any of the speakers or project partners? let me cover that, or any delegates as such. Yeah. Okay. It gives me a personal pleasure, to see what all pain people take to have a good quality fish, a platter on the table, on the dinner table. I'm a big lover, by this community in India. It's a staple food, we typically. The quality, the texture, as a fish eater, we are the best judge of that, I suppose. And this is something we have talked about, how to retain that, the right temperature, and then this is something interesting, Christine. You just mentioned that chilled water transportation of live lobsters to Europe. That's a very novel thought. I didn't realize that has been done. This is a new practice? Is that what you said? This is not routinely done, right? That's what you meant.
Yeah, they are normally transporting it dry, and I think they still haven't seen any new results. But this was a suggestion, and I hope they will continue to use.
Is there an economic study that of course this entails additional cost, but then this also leads to better quality and no death, I suppose. I mean, is there a sort of a return on investment kind of study that this is worth doing? And I suppose people would be doing that.
So yeah, I haven't seen exactly that, but yeah, I think that would be quite rewarding to use that method. And then maybe there might also be new regulations on how to treat animals, and so I think it will be necessary also.
Okay. Anybody has any comments or questions? We'll move on. Thank you, Christina. Thank you again. So we heard from an engineer, and I forgot to mention, and not that I'm supposed to mention, that I'm a mechanical engineer by training. All my academic degrees are in that field, thermal science, so to speak, in terms of advanced degrees and research. It gives me a sort of I don't know what sort of pleasure this is to say that the remaining two speakers are going to be both mechanical engineers, but take it or leave it, but that's the way it is. And how can you have BITS Pilani organized webinar where BITSians, students, graduates of BITS Pilani, alumni of BITS Pilani will not speak? So it so happens that the next two speakers are also BITSians. It's just, I would say, coincidence, because we picked them for what they do, not because they are BITSians, of course, but it's a huge personal pleasure to see that, I personally love working with BITSians for the last 5 years I've been doing. As a matter of fact, let me also share with all the my project colleagues that I'll be completing my term as Vice Chancellor of BITS Pilani in the next 2 days. So on Saturday, I moved back to IIT Kharagpur, where I came from. I was on a 5-year leave, and so it has been a wonderful journey. And okay, I'll remain glued to these projects in whatever form I can. So the next speaker is from the US. We have moved around the world, and again, we wanted to have industry speakers who are in specific expertise from the industry. So we had Ravi from Danfoss from the industry segment in India, the leadership there. And we also had Christina now, who is also from the industry, so to speak, in the research and development from Norway. And now we have Dr. Ravi Ravipati, is the CEO of Churan Mobility, global logistics and supply chain management company that's in Dallas, Texas, close to where I did my doctoral work in College Station. He has 25 years of experience in energy, transportation, supply chain, logistics, and engineering design. Ravi will be talking on reduction of energy consumption in cold chain, of course, something that's close to my heart, I suppose. Ravi is also the Chief Investment Officer of ReValue Capital in Houston, a capital investment company with strategic and direct investments in energy, transportation, and new age products. This company is also engaged in the design, build, and operation of logistics and supply chain networks, which in turn are used by global retailers, manufacturers, and distributors to manage their demand and supply. As I mentioned, Ravi is a BITSian. He has bachelor's and master's degrees in mechanical engineering, MBA in finance, and a law degree as well in industrial disputes. So there you go. If you know why you need to connect with Ravi for all these good reasons. So over to you, Ravi. Let's hear from you on reduction of energy in consumption in cold chain.
Oh, thanks for the warm welcome, Professor Bhattacharya. Can you hear me okay? Okay.
Yeah, it's all good. We can hear you, we can see you.
Oh,
Please
beautiful. Sorry, it's really dark here. It's still 4 in the morning. Let me share my screen. Oh, give me just a second.
No, we are very thankful to Ravi for doing this at such a odd hour. You know, it's 4 o'clock in the morning. It's very, very deeply appreciated. Yeah.
Okay, here we go. Can you see the screen? Okay,
Yeah.
let me get this up and running. Slide view. Okay. Sorry, I'm struggling with Zoom here. Give me just a second.
No worries, Ravi. Take your time. Don't worry.
Okay. Yeah, I'm used to working with WebEx and other things, but Zoom is something. It's it's a new thing.
Enter full screen. Can you do that?
Yeah, it's
there was a button. If just bring that thing back again. There was an enter full screen. That drop down menu you just had. Yeah.
Okay, we'll go with this. Don't worry about it. The idea we'll deal with it. So good morning, everybody. Good afternoon, and well, welcome. Thanks for having me here. Before I get started, I got back in touch with a little introduction before we get started. I got back in touch with BITS after almost 20 years. I came back in touch with BITS to do.
Ravi, can I interrupt? I'm sorry, may I interrupt? On the left top, there is a thing called view. Yeah, and what does it do? Yeah, slide only. That's it. Just click on slide only.
No, it's a slide only. Like, yeah, I just got this new Mac. That's okay.
Right.
Let's leave it. Can you see the screen? We'll go through this.
Yeah, please go ahead.
So you just need to click on the play button.
Yeah, this is. Hold on a second. I'll stop
in the middle.
And do this. Hold on a second.
I think you have unshared. You have to share again.
Yes, I did. You know what? Let's go and do this. We'll deal with this. We'll just a couple of slides. We'll go through this.
Sure, go ahead.
We'll do this. Okay, this is the best representation. So I got back in touch with BITS to do certain things because we're trying to do and set up a freezer chain in India for all the good reasons. And so when I reached out to BITS, and Dr. Bhattacharya said, hey, do you want to do certain presentation? And he said, we're working on certain project and we need a presentation. And I offered him 3 or 4 choices, and he gave me the most difficult thing I ever thought I could do again. After 20 years, haven't touched engineering, to be precise, but I thought I'll do whatever BITS asked. So here we are. The topic, the title of the topic that I gave was the effort to reduce energy consumption in the freezer chains. but the title of the slide deck says it's energy crisis in freezer chains. The reason for this change in title is because the reason we want to reduce energy consumption in freezer chains is because there is an energy crisis going across our freezer chains coming from a business side. Energy has become the most expensive commodity for us, handling freezer chains and also running the freezer chains across the globe. So taking off of that, so I asked one of my partners to give me a best picture to represent the problems that we face in freezer chain today. So, and he said, give me a good picture link. And the picture that you see on the screen is what best represents our problems as an end user in a freezer chain. If you look at this picture, this is how technically it looks in a freezer chain. You go inside a freezer chain with produce and other stuff. Half of them are in a good place and half the produce is not in a good place. And that causes a lot of losses for us as a supply chain manager. And also it increases a lot of risks for us because we are not efficiently using the energy that's available to us in the form of electricity and many other products. So taking cue of this, first, I'd like to thank the previous speakers, Professor Hafner and Mr. Purushothaman, and also Mrs. Weidel for sharing all the insights they had, because they made my presentation much easier. I was preparing to speak a lot about that, but thanks for their inputs. They made a lot of my presentation and my effort easier. So let's move on to the next one. So my presentation is very little on technology, but mostly on business and the business problems we face running a supply chain and a freezer chain, and what we're trying to do to reduce the energy consumption in a freezer chain. So before we head out and ask why we want to work on reducing the energy consumption, as I told you, we have an energy crisis that's going on right now in freezer chain because energy has become a very expensive commodity, both in terms of price, in terms of regulation, in terms of availability, in terms of the new consumer behavior that's coming around. So what are the big things that we are facing today, and what is pushing us to focus on working on energy saving and energy consumption and controlling the energy losses in our freezer chain? The first and the foremost thing is the farm to table timelines. As Professor Hafner and Dr. Ms. Weidel said, fresh food has become a high demand commodity these days. Which used to be a premium product just 10, 15 years ago. Now everybody is demanding a fresh product, fresh produce, fresh fish, fresh meats, fresh fruits from all over the globe. It's like people sitting in South Africa are asking for products, fresh fish from Norway. In fact, we have a warehouse, we have a freezer chain in Bergen, Norway, where we get a lot of our fish from into our supply chain. Similarly, people in Argentina are asking for fish that's caught in Japan. Fish doesn't, it's a fresh produce. So farm to table timelines are shrinking. People are expecting the fish that's as fresh as possible, or fruit and produce as fresh as possible within the matter of 3 days. So right now, the best timelines we're dealing with is people are demanding it to be on their table within 3 days of harvesting, 3 to 4 days. Imagine the pressure people have put on the supply chains. The next is supply chain constraints. As such, the global supply chain has become so much integrated and so much in one piece. A small shake and a small loss in some place, a closed harbor, a closed port, or a closed airport is leading to a lot of challenges, which we'll talk later in the next slides. And the next thing we're facing is, one of the biggest things we face is energy consumption. So as you see in the donut slide, the donut picture there, one of the things that really trouble us, which we really focus on a daily basis, is energy consumption. Because in a freezer chain, if we turn off the freezer or if we turn off the air conditioner in there, the entire produce that's in the pipeline, the entire production, all the products that are in the supply chain will go waste. So we are held liable for losses and also the customer satisfaction. And the final thing that's giving us a lot of trouble, or which we focus on, is trade regulations. As Dr. Hafner said, Kyoto protocols, Montreal protocols, Paris Treaty, all these things are adding a lot of regulatory constraints and how we trade, how we run our freezer chains, what kind of stuff we can put through our freezer chains, how do we handle it. So these are the big challenges that as a business we face running a freezer chain. So if you look at this slide, this is representative of all the things that we talk in a year, all the problems that we accumulate and talk about. So the biggest thing that we are facing right now, which has really come up and bubbled up, is energy consumption. Now people are demanding that we reduce our consumption. Government is asking for it. Consumers are asking for it. So our focus in freezer chains have shifted from many other things into energy consumption and energy reduction. So taking off of that, so what does energy consumption in a freezer chain look like? Sorry, I'm going through a lot of thick slides, but I'll first take you through these numbers, through these issues, and then I'll take you through what we're looking at. So where do we consume the most energy? One is in warehouse and storage, which is a big chunk of it. All our freezer, frozen warehouses and cold chains consume a lot of energy, as in electricity and other stuff. The other thing is carriers. If you look at it, fresh produce, being fresh produce, cannot stay on a shelf. It has to be transported the moment it's harvested or procured all the way to the table as fast as it can. So there is a lot of energy investments, a lot of energy use in carrying the produce and the products from the farm or the place where they're produced to the table where they're consumed. And the next energy consumption point is the transshipment, where it moves from one place to another, like moving from a production floor or factory floor into the a truck, into a refrigerator truck, then coming into a warehouse, then being transshipped from warehouse into another ship, and all this process. The transshipment is also one of the big places where it consumes a lot of energy. And final thing is services. Services is a misnomer here, but essentially it's basically handling of the fish, or handling of, sorry for using the word fish, handling of the frozen produce after it leaves the supply chain. Means it's the last mile energy consumption, where it's brought to the retail store and where it is sold and then brought to the freezer or the fridge in a consumer's premise and stored and used when the time comes. So that's for the services. So these are the four big parts where energy is consumed in freezer chains. And as you see, warehouse and carriers is where most of the energy in a freezer chain is consumed. And that's our area of focus today. So we looked at the problem, we looked at everything, we know where the problem is. So what are the challenges? What are the challenges that are facing freezer chains today from working on managing energy? One is the changing energy mix. It's happening in the US and Europe, not a lot in Asia, but it's coming to Asia, is changing energy mix. Now people are demanding that a lot of non-conventional energy, renewable energy be used in freezer chains. A lot of coal and fossil fuel based energy is being pushed aside, and they're asking a lot of businesses to encourage renewable energy. Then the availability. Energy has become very expensive these days. Electricity, fossil fuels have become expensive, and their availability is getting tightly regulated because of the changing preferences. People are moving mostly towards natural gas and other fossil fuels versus coal and other hydrocarbons. So the availability of a certain product, energy product, has become very difficult these days. For example, there is pressure coming through, regulation coming through to use natural gas in transportation rather than liquid hydrocarbon and liquid transport fuels. Next is regulation. It's in infancy, but right now, because freezer chains and fresh food supply is still 20-30-year-old business, so there's not a lot of regulation on the industry, but it's coming up. So a lot of because freezer chains and cold chains are very energy intensive, governments these days all over the globe are taking direct interest in how we are spending our energy, how we consume our energy. So that's just coming up. It's still not at its full force, but everybody started taking a look at it. The next big thing is consumer awareness. People have become really aware of where the energy is getting used in the products they're consuming. Classic example, now people are end consumers are demanding how much carbon has been produced or has been used in the product that they are going to buy or procure from the product floor. For example, these days there is a lot of branding going on consumer products to the amount of carbon that's produced in making a certain product. Classic example, recently a retailer in the US called Costco started putting the total amount of carbon that's produced or carbon that's generated on a packet of salmon, frozen salmon. So starting July, they're going to put the branding on the salmon that's being sold in the freezer chain, in the freezer section of Costco. Excuse me. So consumer awareness is driving a lot of energy choices in freezer chains. Next is, of course, cost. As a businessman, as a business, cost is very important for us. Energy cost has really doubled and tripled in the last 15 years because the mix is changing, the availability is becoming a risk, and lot more people, lot more consumption is being people are consuming a lot more energy than what it was 10-15 years ago. So the cost has substantially gone up, and running a freezer chain has become a very difficult thing these days because of the cost of energy. And finally, and one of the things that's coming up these days is people are pushing supply chains and freezer chains in special to start using sustainable sources of energy. Both energy mix and sustainable sources of energy go hand in hand. So they're asking for solar energy, the solar wind energy, and other renewable energies to be directly used in freezer chains, and not coal or fossil fuel based. So these are the challenges that many freezer chains are facing today. Cost being the most important one, but rest of them are showing up and making their presence felt in all the choices that are being made in setting up and running freezer chains. So moving on to the next one. So what are we doing to reduce energy consumptions in freezer chain? So we looked at the risks that are involved in it, we looked at the challenges, and now what are we trying to do to reduce the energy? This is a huge topic, but I'll try to take everybody through it quickly because this topic itself can go for hours. So the first thing we're trying to do is redesign our freezer chain networks. Putting a freezer chain is a very expensive proposition because once it's laid in the ground, changing it, altering its alignment is pretty hard. So what we're trying to do right now to reduce energy is positioning our freezer warehouses in such a way that the transshipment costs and the carrier costs come to a minimum, in the sense they can be managed, measured, managed, and controlled. The next thing we're trying to do, which we're spending significant amount of our capital investments these days, is new warehouse and storage designs. So since the Paris Accord, a lot of constraints came around, a lot of regulations people started putting a lot of regulations together on how a warehouse and a storage should be. So earlier, a freezer chain or a freezer warehouse used to be a big box warehouse where the entire thing was frozen to death, with no regard to the kind of product that moves through it, the kind of effort that's made to manage multiple product lines into it. So the new way, we're trying to come up with new warehouse designs where it includes both, as Dr. Hafner said, mid-level, low-level, and high-level freezing. In the sense, it's like a Russian doll, where you have a deep freeze zone in the center of the warehouse, and it's enveloped by a mid-level freezing freezer warehouse, and outside it's enveloped by a regular cold storage. So we're coming up with a new warehouse design to manage the energy consumption and energy reduction. And next is the storage design. Like, how do we design, how do we move the product through the freezer chain and modify the warehouses to have multiple products? So that's the biggest thing we're investing in. And the next and the most promising thing that we're working on since 2018 is, as Dr. Hafner said, is full freezer chain lifecycle energy management. So in one of the slides, he mentioned co-locating a food processing facility along with the freezer chain. So we recently did built a freezer warehouse, frozen warehouse, where we use the cold side of the business to freeze our warehouse, but the hot side of the business, which is the hot energy, the energy that's thrown out into the atmosphere, that is now used by a soup manufacturing company. This is a company that manufactures soup in the US. So they are using the hot side of the refrigeration equipment, and we are using the cold side of the equipment. So we're trying to co-locate mutually beneficial facilities, and we're coming up with an idea of full energy life cycle management, rather than just worry about how we freeze our warehouse, rather than struggle with what do we do with the leftover energy. So as Dr. Hafner said, that idea of co-locating two different businesses, two different product lines together, has taken up a significant attraction and attention. And the Paris Accord especially rewards businesses who can reduce the amount of energy that's being consumed. And this is one of the things we're trying to do since 2018 to maximize the energy that's being consumed in the freezer chain. Following that, it's co-located facilities, just exactly as Dr. Hafner said. We use the cold side of it, and we find a willing partner who is ready to use the hot side of our refrigeration to either bake bread, make soups, and do other processing. Like recently, there is a tuna processing facility where they cook tuna with the tuna which we store in our warehouse. So this is a co-location of the facility where two businesses, two different product lines get together, and we maximize the resources. The next thing which we are bringing in to reduce the energy is multi-product strategy. Wherein right now, if you look at many freezer chains, they either handle produce, vegetable produce, or meat produce, or milk, or ice cream. So they're distinct because for various reasons, for regulatory reasons, for contamination reasons, for consumer safety reasons, we don't mix products. But with new warehouse designs and storage designs, we're able to manage multiple products in single place, rather than building a high freeze warehouse just for meats, and a medium freezing location for produce, and a low freezing warehouse for milk and other dairy products. So we're able to put everything together with new warehouse designs, so bringing multiple products to a single freezer warehouse, a freezing chain, rather than multiple chains. So that's how we're reducing the consumption, because the real estate goes down, the amount of energy consumed goes down, and which is the cold part of it is used effectively. The number of truckloads gets reduced. So the whole effort goes into this multi-product strategy, which reduces the total energy consumption of the freezer chain. And finally, which we have been investing, the final topic is new freezing and cooling technologies. This topic itself is worth a presentation, but as Dr. Hafner said, we are coming up, we are investing in new freezing and cooling technologies. As Dr. Hafner said, using carbon dioxide, using probed cooling, or like pocket cooling, or other technologies. So this is one. What does it, quickly to the last but penultimate slide, is what does it give us as a freezer chain business owners and a business running freezer chains? It gives us the best thing, which is reduced energy bills, which is money for us. It reduces it lowers the ownership costs, and it's giving us a lot of carbon credits, which we trade, which is the biggest commodity these days for a lot of energy companies. Next is high freezer chain availability because we have multiple products. The next is the gross product movement volumes. We're able to move a lot more volumes because of multi-product strategies, and freezer chains, a lot of energy reduction happens because of that, and we're seeing a lot of advantage in that. And the final two are which are of reason for the consumer interest, which is earth and environment impact, which people are demanding a lot these days. And then the last and the final thing is goodwill, because we are becoming more energy efficient and we're getting good brand name. People are end users are willing to use our freezer chain. And the final thing, which is the last minute, is something called TOCA. Which is coming up a lot in freezer chains and supply chains these days because of the Paris Climate Accord. It's the total carbon add. Like, how much am I responsible? How much carbon am I adding to the entire life cycle of the product? So people are demanding that everybody identify their total carbon add, and the industry is moving towards 3% TOCA, which is from the point we pick up produce or the product from the manufacturer or the farmer to the point we get it to the consumer's freezer. We should not be responsible for more than 3% of the total carbon add. So this is our industry goal. This is what is driving our energy consumption targets and energy consumption outlook, and all the things that we're trying to do today. So this is what the industry mantra today is. Yeah. So any questions? Sorry, I went through a lot.
No, it's okay. Thank you, Ravi. Wonderful view there. I think we have some comments. Let me come to those. Yeah, Ravi, you see the iconic clock tower behind me? Reminds you of your good old days?
I do, sir.
Great. So there's a comment from Shankar Subramaniam. India imports a large quantity of LNG into many of our ports, and regasification of this LNG could provide abundant refrigeration for freezing and storages. Can we not think of in terms of using this free energy cooling, whatever, for our freezing and storage needs? Don't know if it is directed toward you, but you want to address that? That's one. There's another one, something different. Maybe Armin has an answer to that. Armin comes on.
Yeah, I mean, the utilization of this coal from LNG is a brilliant idea. The infrastructure is a bit complicated, but it's doable. So if there is a will to utilize megawatts of freezing capacity, and if you have the synergy with nearby storage facilities, production facilities, is a no-brainer.
It's actually an investment, not much of energy input as such. It's
the energy has been done in the other places where they liquefy it.
So I'm saying so in terms of return, in terms of COP, etc., it will be a fabulous number. No real system can give you this sort of COP. Okay.
We have looked in this kind of systems in Spain or so, And if you have a contract with that company providing you that LNG for the next 20 years, the investment is really big.
Absolutely, yeah. The other comment I have, the idea of having the freeze temperature in center with talking about the warehouse design Ravi referred to, layers, Russian doll you said, in center with medium temperature around it. When you say around, it's length and width only or of height also? And then a follow-up, secondly, in India, we are also trying to utilize the superheat. Okay, Ravi, you want to throw some light? I don't know if it conveyed.
Yeah, I'll take 30 seconds to answer all three questions.
Ahead, please.
The first thing, there is nothing called free energy. So as Dr. Hafner said, somebody is like, I work with Sabine Terminal here in Houston, which liquefies natural gas. We have some investments there. So they put in a lot of energy to liquefy that gas, right? So there's no free energy. Somebody is paying for it. So once the tanker reaches, as Dr. Hafner said, if there is somebody willing to re-extract that energy that's already put in there, it sure is a good energy source. As such, natural gas is a coolant people use. Methane is a coolant people use to liquefy and freeze stuff. So it's a double advantage, but it needs investments and I would say a long-term plan to leverage it, because it can be a one-day thing. And so it's a good source of energy. So it's a free energy that we're shipping from US to India when LNG comes to the port in India. So, but it's a long-term plan. Somebody has to, as Dr. Hafner said, somebody has to step in, make a long-term plan, invest in it, and extract the energy that's already put in there. So like we're doing it, putting a soup kitchen next to our cold storage warehouse. So it's a plan. Somebody has to work it together.
And we need to also identify who is going to invest, because is it the port? Is it the importing agency? It's a bit of a diffuse situation there. There are multiple hands working there. And as you said, we got to have a long-term plan. Otherwise, it's.
Yeah, but sorry, as long as there is money to earn, there is always somebody. And it is really a no-brainer, but somebody has to do it. And nowadays, I guess they utilize the seawater to gasify all the gas, because it had to, before you put it in the pipeline, they have 30, 50 megawatt of cooling or heating, which is provided by cooling down the bay. It's good for the fish.
That's right, yeah.
Waste of energy.
The next one, I'll quickly for 30 seconds, the idea of freezing temperature in the center and the medium. It can be picturized like that, but it all depends on the kind of products we move through the warehouse, because it's not perfectly set in the middle. There's a box around it. There's another box around it. It can be imagined like that, but it's close to it. 70% it's close to that idea, but it also, the kind of products we move through the freezer chain also fixes it. For example, we built a freezer chain like that, a frozen warehouse like that in Memphis, Tennessee, where the actual frozen section is under the ground. And there is a cold storage on top of it. And there is a soup kitchen, for lack of a better word, next to it. So it all depends on the design, but technically it's a box in a box in a box, where we kind of use everything rather than putting 3 different boxes and freezing it at different temperatures and losing all the energy. Yeah, but yeah.
Okay.
And superheat. Somebody said superheat, Dr. Bhattacharya.
Yeah. Secondly, in India, we are also trying to utilize the superheat. It's the same gentleman, Aftab Sharif, who asked us these 2 questions. Yeah, go ahead, Ravi.
Okay. I remember somebody trying it in 2018, but financially it's not viable. The technology has, the idea hasn't reached a point where it can replace something else at the same cost of operation today. And in a business sense, not on a technical sense, but if I'm as a businessman, I'm trying to see if I can replace my existing refrigeration technology with this. It's not financially viable for me to do it today. So it's not really there yet.
Well, Ravi, thank you so much. I can't thank you enough. I hope to see you soon. And we have Dr. Maitri Thakur and Professor Srikant Rautroy, our supply chain experts in our team. There are others, I'm sure, but these two are leading the efforts along with our students. And I hope we get to work with Churan, your company, and sort of take it forward, not just for seafood, for any other generic issues, in terms of supply chain in India.
Thanks for
okay, I'll close, Ravi, your session here, and we have in the interest of time, we have our last concluding speaker. This is, the BITS Pilani team is led by three of us, Professor Srikant Rautroy, myself, and Professor Manishankar Dasgupta, our next speaker. So let me introduce, I have the pleasure of introducing my head of the department. That's the mechanical engineering department of BITS Pilani campus. And, he has been at this for 27 years now, did his undergraduate mechanical from National Institute of Technology, Silchar, masters from where I studied my undergraduate, Jadavpur University, Calcutta or Kolkata, India, and he did his doctoral work at degree also from BITS Pilani. Primary research interest, he deals with in environment-friendly technologies, particularly transcritical CO2 systems for HVAC applications. He also works in the areas of mechanical engineering design and sports engineering. Quite a bit of a cross-discipline effort there. Professor Dasgupta is going to actually present our part of the work that BITS Pilani experience on the ReValue. And Professor Dasgupta will speak for about 10 minutes. And this session will not have a Q&A. After that, I'll have closing statements. Yeah, Professor Dasgupta, over to you.
Yeah, thank you.
Hey. Yeah, go ahead. Yeah, we can see it. Can make it full screen. Yeah, just down below. You have this button
I hope I'm audible.
Yeah, you are audible. It can be a little louder, but can you make it the button at the bottom, the full screen thing?
Yes.
Bottom, at the bottom of the screen, next to the Zoom slide. Yeah, that's it. Yeah, go ahead.
Yeah, I hope I'm audible.
You are, just you can be a little louder. Yeah.
And I hope I will do justice to the 10 minutes allocated to me for this last bit of presentation. Dear participants, I welcome all of you to this last leg of the webinar, wherein I will present about the BITS experience in the overall project, in the Norwegian project, which is nicknamed as ReValue. We, in fact, have great achievements through this project, and apart from a lot of learning for ourselves. In this ReValue project, I had the privilege of working under the leadership of Professor Shouvik Bhattacharya as project PI, and my dear colleague, Dr. Srikant Rautroy, as who has immense contribution to this project. I also appreciate the contribution by two of our research scholars, Mr. Santosh and Mr. Abdullah Sultan, in the project. We had industry partner named Kaiko Surimi from Mumbai, and Mr. Asif Nayak and his team assisted us in collecting primary data. We had project partners from Sintef Norway. You have heard about, from them today. We had from MIT University, and then this Grupo Carinza from Spain. If we bullet pointed the achievements or our achievements through this project here. So we can highlight a couple of things. We added a lot of domain knowledge in surimi cold chain in India, and that means we collected a lot of primary data in this field. We have trained manpower, 2 research scholars, and we have established a lot of external links in terms of industry and laboratory connections. We calculated the carbon footprint for this process of surimi production in India. We proposed some of the novel refrigeration systems, which are designed dedicatedly for specific food supply chain processing and storage application. We also have worked on low GWP alternatives, and we had heard a lot about in today's discussion about CO2 transcritical system and CO2 NH3 cascade system, and we worked on them. If we look at the fishing scenario in India, it is predominantly by small fishing boats, which are powered by diesel engines, and we saw some opportunities there. It is quite unlike those which are discussed by Professor Hafnan and Professor and Dr. Krishna, wherein they discussed about large trawlers having dedicated refrigeration system within. But these are small boats, and they generally carry ice, or rather crushed ice, in their compartments within the boat. And we analyze their energy footprint, and we see that about 28% of the exhaust gas heat is lost to the surrounding. We saw some opportunity in them, and then we designed a vapor absorption based system utilizing this exhaust heat. And this work we presented in a conference, which is IHSMT conference in IIT Roorkee. Here, this system is a compensatory refrigeration system, in the sense that whatever heat ingress is there to the iced compartment from the surrounding, we are trying to cool that much amount by utilizing this refrigeration system from the ices, and then keep the ice for longer period, and then assist in quality, maintaining the quality of the fresh harvest. We then focused onto the onshore processing plants. In India, the processing plants generally are mostly ammonia based. They have multiple evaporators, as we can see from this diagram. This is because in seafood processing and storage, there are requirements at various temperature, from large quantity of chilled water, which is generally required or supplied at 4 to 5 degrees centigrade. Then there is large requirement of ice. Then there is requirement of long time freezing and storage, which is generally at minus 20 degrees centigrade. And then quick freezing requirement, either through blast freezer or plate freezers at about minus 40 degrees centigrade. So these are typically met with a single ammonia-based plant. And since most of these seafood processing industries are located near the coastlines, the temperature throughout the year remains very high in those regions, which is about 35 degree plus. And then for which, as we can see, the cascaded systems will give better efficiencies. And we designed at least 3 cascaded systems, CRS 1, 2, and 3, as represented here, with elaborate design, and then tested them for various seafood applications. Some of these we have found out better for application in surimi. Some of these we have found better in application like fish fillet and then prawn industries. These results we have communicated to a paper in the IAR journal. Next, we invested our effort to improve the performance of the cascaded system. And then we introduced several changes in terms of internal heat exchangers, gas coolers, etc. And then improved the performance of the conventional NH3 based system to the cascade NH3 CO2 system. And this results we have presented in 2020 at Gustav Lorentzian conference at Kyoto, Japan. Currently, in this line of work, we are working on a couple of low GWP options for HTC, that is high temperature circuit, and the low temperature circuit of the cascade system. We have about 8 refrigerants we are testing in the high temperature and about 5 in the low temperature. And there is some early result with the annual energy consumption basis for the environment condition at Mumbai, which remains above 32 degree in major part of the year. And we have certain good response. Now, annual energy consumption is not the only parameter. We have to also look at the cost of the refrigerant, cost of the system, regulations around availability of the refrigerants and so on. So all these are being analyzed nowadays. And then soon we'll have some publication to report with this research area. We extensively mapped the surimi supply chain through our primary survey at various coastal regions in Mumbai, at Sosundak, Mumbai, at Ratnagiri, Gadre Marine, and then at Udupi in south of India, where we have RRM processing, rest of material processing plant, etc. And then we, through this process, we have identified about 81 major activities which are identified in the surimi or fish handling. And we have come out with a lot of green measures for improving the supply chain efficiency. And then we have measured the share of the activities in terms of energy footprint. And these outcome we have reported in the Journal of Cleaner Production, and which is available in public domain. We also extensively worked on the supply chain response metrics in terms of certain specific scenarios in which we have utilized, as we can see in this plot, various as-is condition as the fish is handled in the dock, or right from the boat and then to the processing plant and afterwards to the plate, as it is said. And then this, of course, is done only for the supply side here. And then we have utilized certain established techniques to and visualize certain improved scenarios which can be intervened in the supply chain to improve it. And if we focus onto this, we can look at the proposed kaizens, which is on the right side of the chart. And these are some of the interventions which we propose based on the studies that we have conducted on the seafood supply chain. And this can give us immense benefit. And all these scenarios has been extensively studied, and we have reported it in a journal paper. We also worked on the LCA, or the life cycle assessment, which is an extensive work in terms of gathering primary data from different points and also availing secondary data through some software. And we assessed all this in terms of major activities and then their carbon footprint. And then we are able to map the carbon footprint of the Indian surimi supply side. The carbon footprint right now, the present condition, it is assessed to be 3.86 kg of CO2 equivalent per kg of fish, which is harvested. We studied some partial integration scenario because, as our previous speakers have discussed, the a big challenge in India is that the supply chain is not well integrated, but are very much fragmented. If we can in a short time establish some partial integration, we will be able to save a lot of carbon footprint in it. And then if we can go for complete integration, we have analyzed all those scenarios. So these scenarios has been, and LCA has been reported, and it is accepted for publication in a journal, as you can see at the bottom. As a project deliverables, we had published 3 major reports which has ISBN numbers, and then they are available in public site. And you can always, interested parties can always go through them. And then if you have more queries, we are available to answer them. And to your queries, we will basically love to do that. Because in this work, we are, some of this work will be extended with the help of our students and with the help of funding support from external agencies. And then all of your support and encouragement is very much welcome. I thank you, all of you, for your patient hearing. And I don't actually have a dedicated question answer time reserved, because it is already about 5:30 now. And then if you have any query, please feel free to mail me. And then I'll be more than happy, myself and my team will be more than happy to answer your query and establish contact. Thank you. Thanks, all of you.
Professor Dasgupta, thank you so much. We have a message from on the chat, in the chat box, to provide valuable feedback. There is a forms available. There is a link for you to please do that. It will help us in understanding and do better work. This is time for me to close this this webinar. You know, a wonderful support from many people. I want to thank them. Maybe name a few key persons, and we are, you know, almost in the last leg of this project for several years now. And I want to, first of all, I want to thank everybody who attended today in spite of all the difficulties. And yeah, it was not too short, it was stretching the time, so I want to be brief as well here. And I want to thank, I'll start with the Norwegian side. I'll thank Maitri and Christina, of course, who spearheaded, among others, this project. Of course, Maitri is, as I said, she is the boss. We must remember that. And then I want to thank, right away, I come to the Indian side, you know, Professor Nutan Kaushik, who used to be in TERI, now in Amity, and has been, and of course, Rasa back in SINTEF as well. Many others, you know, we have the friends in Carinza, Spain, friends from there. The BITS Pilani team, Professor Dasgupta, Professor Manishankar Dasgupta, you just heard him present. And Professor Dasgupta, thank you. Thank you for covering the BITS Pilani story very meticulously. And Professor Srikanth Rautroy, also in the Department of Mechanical Engineering. I can see Nutan now. It's good to see all our good team members. And I want to mention a couple of things. You know, of course, we publish, you know, this is what we do from the academia, and disseminate information. And this was one such effort as well. We also work on human resource training. We do that. That's very important aspect of our life. We create skill sets. So we have doctoral students in Amity, and we have Abdullah and Santosh. I want to thank them. They have done, Abdullah was, I think, coordinating this this whole Zoom handle, and many others for helping us out on this. So what happens, I know today PhD graduates of BITS Pilani and graduates from my parent institute, IIT Kharagpur, doctoral students, they are working in Norway today. It is also a kind of a supply chain, if you will, that we work on the value chain. The value is important, and then we want to keep the rigor going, and so that the quality of the products that are traveling in the supply chain, they are maintained well. We would like to continue to do that. The industry partners are very important. I want to thank Kaiko Surimi in Mumbai for having helped us, and many other companies for the other partner institutes. I will hand it over to Professor Dasgupta for a minute, and Professor Srikanth Rautroy. Anybody wants to speak quickly, very briefly, and finally back to Maitri if she has something to say as a closing statement. And after that, we close this webinar. Professor Rautroy, quickly, a quick comment from you, if there is any.
Thank you, sir. This is quite interesting and informative lectures from industry and the other researchers. Thank you.
Okay. And Professor Dasgupta, did I miss out on anybody? We should be mentioning names, people who contributed. There are a lot of people in BITS Pilani in the background. They helped us in organizing this, I'm sure. But Professor Dasgupta, go ahead and briefly mention anything.
In the whole process, a lot of people has helped us, and today's administering today's webinar also. And we got a lot of help to conduct our surveys in Mumbai dock, and it is a challenging place. As Ravi also mentioned, it is a very challenging place. And then they provided us, accompanied us for the survey and then all the processes. Thanks to all of you. And dear participants, kindly provide the feedback.
On the link given.
Pasted the link a couple of times, so please feel free to click and then provide your feedback. This will help us in the future to organize things better. Thank you.
So Maitri, over to you, and then I'll have a final word.
So I would like to thank everyone that attended today, and also thank you to the speakers. We had very insightful presentations, and I hope we can continue the collaboration even after this project ends. Thank you.
I join Maitri in thanking the speakers, of course, as well as the delegates and all the attendees. Thank you all, everyone, and we'll see you soon. As a couple of things, we have another one coming up. We'll be in touch. We'll send you detailed information as soon as the dates, etc., are frozen. And of course, Christina also mentioned the Gustav Lorenzen conference in Trondheim next year. Wonderful. Take care. Things are still pretty tight in India. Things are not so good in India still, and I guess things have improved in other countries, but please take care of your near and dear ones. So this is the final word. Thank you all. Bye-bye.
Thank you, Sabik.
Bye.